In this lab, we'll be analyzing op-amp circuits. Let's start by deriving the equation for gain for a non-inverting op-amp. So to find the gain, we need to know the relationship between Vout and Vin. Now a good place to start is knowing that R1 and R2 are arranged like a voltage divider. And knowing that V plus is equal to V minus, we can say that Vin is equal to R1 over R1 plus R2 times Vout. And this is just the voltage divider formula. We can further simplify that to get a gain equal to 1 plus R2 over R1. So now let's actually create an op-amp circuit using our Arduino. So here in the middle of our breadboard, peeking behind these wires, we have our op-amp. And this is the potentiometer we'll use to adjust the V input. And we'll be using that so we can test the responses of the different terminals, which are probed using these colored wires, at different voltage inputs. And for this first circuit, we're going to be doing a unity gain amplifier. So we're going to bridge the inverting input with our V output. And that's what this gray wire is doing right here. So real quick, going over our Arduino code, all it's doing is it's taking the values read from the analog pins, and it's going to write them to a string which will feed into processing. Now our processing code is going to take those values, and they're going to plot them onto our oscilloscope. So going into here, this is our unity gain amp, and basically it has a gain of 1, which means our V out is directly proportional to our V in. And that's exactly what we'll see when I move around the potentiometer. Our V in stays with our V out. So now here's the inverting amplifier circuit. Now a couple things to note is that over here we have a voltage divider, which is made up of two 1K ohm resistors, and that'll feed 2.5 volts into our non-inverting input. And that's going to be our new ground, quote unquote. And then we also have, bridging out from our inverting input, a wire that connects to this 10K ohm resistor, and that's going to feed into our output voltage. Here we have the oscilloscope view of our inverting amplifier. So as I move the white dot around, our Vin, and I'm moving it in like really small amounts, but we can see that our blue dot, our V out, is moving a lot more sporadically, and that's because we applied a gain of a -10 to it. This is also why as I cross the yellow line, this threshold right here, it also crosses the threshold in the opposite direction, because we're trying to invert the signal. Now let's analyze an integrating amplifier. So from the diagram, you can see that now we placed a capacitor between our inverting input and our V out. So we can say that V out is equal to negative voltage through the capacitor. And we know that the formula for voltage through a capacitor is equal to 1 over C, which is the capacitance, times the integral from 0 to t of the current going through that capacitor. And we know that since the inputs of our op-amp, the current is equal to 0, we know that the current going through that capacitor is all the current from that V input and the resistor. So we can say that I is equal to V in over R. So plugging that now into our formula, we get V out is equal to -1 over RC, which is the resistor R and the capacitance of our capacitor, times the integral from 0 to t times V in. And this is what the circuit looks like. Not much has changed between this one and the inverting amplifier, but we did change this resistor with a 4.7K ohm resistor, and we also replaced the 10K ohm resistor with a capacitor right here. So going back into our processing window, this is the oscilloscope view of our integrating amplifier. So the first thing you'll notice is that when I cross over this 2.5 voltage threshold, it inverts V out. But then also, if I keep it I can keep it at 0, and we see that as the capacitor discharges, we get that curve downwards, which we saw in our integral relationship.